Professor Mark Trodden with Particle Physics and Cosmology.
Can you hear me okay?
Yes. Yes.
I tend to be very loud, so you're probably going to have to drop that down, or people will. It's okay. Yeah, it's making you deaf. Good morning. Thanks for inviting me. This is a great place to have a conference. It's almost impossible to focus on your work, but I'll try for at least an hour. So my talk is going to be, I think, quite different from the ones that you heard yesterday, in the sense that most of the other talks that you're getting, most of the other lectures you're getting a sequence of talks from are talking about really sort of physical cosmology issues. And I'm going to try to talk, Eric asked me to speak about the connection between particle physics and cosmology, which, if I really took it seriously, you would just be in here for the next year. So I'm not going to do that. But what I will do is I'll try to use several of the major questions that are facing cosmologists today as a sort of playground to discuss a number of ideas that connect particle physics to cosmology, and particularly, at least in the first couple of lectures, that connect them to upcoming experiments, and in particular the LHC, although I will only peripherally touch on that. So if we take this, just to sort of get started and orient us, modern cosmology has many open questions, many of which are associated with this sort of pie chart that you see everywhere that lays out the abundance of various types of matter and energy in the universe. So 4% of the universe we know is made of atoms, if you like, or at least baryons, the stuff that we're made of. And today, lecture one, I'm going to talk about that. So the great thing about baryons, of course, is that we know what they are, which is a unique situation to be in cosmology, since we have no idea what the rest of the universe is made of. But they do pose a deep, profound question for fundamental physics, and that is, why is there more matter than antimatter? And that's what I'll spend today talking about. And I'll use that to lay out a set of connections involving phase transitions and non-perturbative structure of gauge theories and other such things as I go along. Then there's the stuff we call dark matter, more complicated, something we don't know what it does. What I'll try to convince you in my second talk, which I think is on Thursday, is that we do have some fairly well-motivated candidates for what dark matter is. And by well-motivated here, I mean arising from sensible theories of particle physics that contain new particles for reasons other than the fact that we would like to invent a new dark matter candidate. So I'll try to get at that in my second lecture. And most of the material in here, I think along the lines of what Lucia and Ed said yesterday, and Martin, is quite old and more standard stuff. It's mostly important and relevant today because of upcoming particle physics experiments. And then, so there are other questions associated with dark matter here that other lectures are addressing. And then I'll move on to this thing called dark energy in my final talk. This is, of course, much more complicated, and we really have no idea what it is. And in lecture 3, what I'll try to do is focus on, rather than talking about a cosmological constant and why it's so small, and rather than talking about the question of whether cosmic acceleration is a breakdown of general relativity in 4 dimensions, which is I think something that Ev will touch on, I'm going to ask the question, what kinds of particle physics theories can give you some form of cosmic acceleration. And in particular, I'll focus on theories that arise in extra dimensions, so-called DGP models and induced gravity models. And I'll use those to, in course, talk about a set of 4-dimensional effective field theories that people have been interested in the last few years, called the Galilean theories. And that's something that's very, very current. And so hopefully I'll be able to get to that by the end of lecture 3, which is on Friday. There are, of course, a whole bunch of other questions in cosmology, all of which connect particle physics in a deep way, cosmology, and most of them are involved with origins. Why is the universe so flat? Why is it so homogeneous? Why did we get in a low entropy state? Does something resolve the Big Bang singularity? There are other things I could write down here. And all of these are completely other topics which would be perfectly fine to come under the title that I was given, but I'm not going to talk about any of them. But I will be around all week, and I'd love to talk to any of you about any of the questions that are on here or anything else. Okay, so as I said, essentially all the questions that I raised on the last slide have called for a fundamental physics solution. And in many of them, perhaps not all of them, most of them, it's the interplay with particle physics that's the crucial ingredient. Something that you, at least initially, would not have thought, that when you look at the night sky, you look at structures in the night sky, you look at the contents of the universe on large scales, you would not normally have thought that it would be the physics of the microscopic that was really responsible. And as we'll see in the next few lectures, that's a crucial part of modern cosmology. So, as I said, I'm going to focus on three major problems: the baryon asymmetry, dark matter, and cosmic acceleration. And I'm going to use them basically just to tour some popular approaches to each of them, and in doing so, explore various ways in which particle physics makes contributions to these questions. And my goal, just to be clear here, is not to be comprehensive, and it's going to be hard to be deeply pedagogical in 3 lectures in PowerPoint as opposed to on a blackboard. But I think the point of the conference is that we're supposed to have time in the discussion session and over dinner and everything else for you guys to talk to me or to yourselves about these issues. So I strongly encourage you to grab me and make me talk to you during the coffee breaks, during dinner, etc. I'd like to do that. Okay. Okay, so my outline today, I'll try to convince you very quickly why the existence of matter over antimatter is a problem at all. It's something you should worry about. Then we'll go on to some candidate models that purport to describe why the universe is dominated by matter over antimatter. And in particular, those that are motivated from particle physics. I'll very briefly talk about baryogenesis and grand unified theories. This is the original way in which people thought about this problem. It's still relevant today, although I will just comment on the outline of how that's supposed to work. And in questions at the end, if you like, I can come back and tell you some new twists on this that have been realized in the last decade or so. But what I really will do for almost all of today is talk about electroweak baryogenesis. And I'll talk about phase transitions, anomalies, CP violation, etc., etc. And the reasons for this are multiple. Firstly, I think it's a very beautiful idea. It ties together some interesting mathematics with some interesting particle physics with some interesting cosmology. Also, electroweak baryogenesis has a great advantage that all the relevant physics is accessible at the TeV scale. And the TeV scale is where our current colliders sit. It's what the LHC is designed to probe. And so this is a particular well-motivated model in which you may produce the observed abundance of antimatter, of matter over antimatter in the universe, and may be able to test all aspects of it in a controlled experiment here on Earth, and that's quite remarkable. If I have time, I'll speak about leptogenesis, just because talking about baryogenesis naturally leads into it, and also because it's another example of a well-motivated particle physics model that has become, in fact, even more well-motivated since the discovery of neutrino masses. And it relies crucially on some of the structures that I'll talk about in the electroweak part. So as I said, I'm going to focus mostly on this, although I'll mention these other ones in passing. Okay, so why do we care about this problem at all? So there's a fundamental problem in physics, which is that you can construct a ladder of evidence that very quickly tells you that the observable universe is made almost entirely of primordial matter and not antimatter. Okay? So you can start by doing experiments on Earth. This is Dirac. This is Dirac, who told us about antiparticles. This is Feynman. And you'll notice that their feet are touching. So from this picture alone, you know that Dirac and Feynman, although you might believe they were made of different stuff than you, are in fact made of the same stuff as each other. And the fact that they're touching the same ground that you touch tells you they're also made of the same stuff as you. So that's quite reassuring. We're all made of one type of stuff. We're made of matter, not antimatter. Now, this is a very easy thing to extend. After all, we've sent people to the moon. They didn't explode. And therefore, they're made of the same stuff. The moon is made of the same stuff as we're made of. NASA sends probes to other planets. Most of the time they don't explode. Occasionally they do. But it's not because of the reason that they're made of antimatter and not matter. And you can probably see quite quickly that this chain of reasoning can be extended out to very large distances. And remarkably, you can ask the question, if there were large regions of our observable universe that were made predominantly of antimatter and not matter, what would you observe in the sky? And it turns out that a combination of high-energy gamma rays that would result from interactions of the matter domains with the antimatter domains or distortions of the microwave background, depending on which energy range you're talking about, is enough to tell you that the observable universe up to essentially the Hubble size is made essentially of all matter and not antimatter at all. Okay, so this particular argument that takes out the Hubble sizes in a nice paper from quite some time ago by Cohen, Rubel, and Glashow, I think is still completely relevant today. Now, we can do a little bit better than this because, while you can argue qualitatively, as I just have, that antimatter is essentially negligible in the universe, we have a very good quantitative measure of this as well. So the lightest elements, as you well know, deuterium, helium-3, helium-4, lithium, were produced through fusion processes in the very early universe, and of the order of minutes after the Big Bang. This is, by the way, our earliest direct test of the Big Bang theory. Now, how that happens is sensitive to a number of different things, the expansion rate of the universe, etc. But in particular, it's sensitive to the amount of matter over antimatter in the universe. So the relevant thing that I'll refer to in this talk is this quantity eta, which is the number density of baryons, protons, neutrons, minus the number density of their antiparticles, normalized by the entropy density in the universe, roughly speaking, the number density of photons in the universe. Now, sometimes it's convenient to move this into essentially omega baryon, which is another way of thinking about this. So omega baryon, you know, is defined this way, H in the usual way. But what does data tell us? So here's a plot of the abundances of the light elements as a fraction of the hydrogen abundance against omega BH squared. And what you're seeing here are essentially simulations. You put in a particular value of omega baryon, or if you like, the excess of matter over antimatter in the universe. You run well-known nuclear physics processes from the laboratory through a computer in an expanding universe, and you ask what abundances of each thing are made. And the remarkable fact is that all known measured abundances lie in this yellow region, and they all lie in, I mean, it didn't have to be this way, right? You could have had the observed helium abundance here, the observed helium-3 one over here, the lithium one here, but they all lie in a common line that point to a particular value of omega baryon. And in fact, as you well know, people in this room know much better than I do, you can do a similar thing these days from comparing the ratios of the peaks of the microwave background power spectrum. The answer you get is omega baryon H squared is about this, and the big question we have is how did this arise dynamically? In the context of the number I showed you on the previous slide, the number density of baryons minus the number density of antibaryons modulo the entropy density of the universe, the number is of order 10 to the minus 10. It's relevant here. Somewhere between 3 and 7 times 10 to the minus 10. So the goal, therefore, of baryogenesis is to understand how a well-motivated particle physics theory, in the context of an expanding universe, can generate that value. Since the early universe was incredibly hot, you would expect it to be populated by baryons, antibaryons in large numbers. So how can it do this while remaining consistent with all other particle physics and cosmological data? Now, back in the late 60s, Sakharov told us what particle physics theory would need to do in order to have a chance of generating a number like this. So what do you have to have? Well, the first thing is that you have to violate baryon number. Your theory has to be capable of changing the numbers of baryons in the universe. This should be clear. If it doesn't change the number of baryons, it's certainly not going to give you a way to generate a given number from it. It's also important to violate both the charge and charge parity symmetries. This is because if you have a theory that can violate baryon number, there'll be processes in that theory that produce more baryons than antibaryons. And there'll be other processes that produce more antibaryons than baryons. Both of those processes violate baryon number. But if you don't violate these discrete symmetries in particle physics, then on average, those interactions will just cancel out. And the total number density of baryons at the end will still be essentially 0. So you need the violation of these discrete symmetries to bias whatever interactions are happening in one direction over the other. And finally, you need to depart significantly from thermal equilibrium. There are many, many ways to see this. Of course, the easiest thing to say is that if you're in thermal equilibrium, nothing happens. Now, that's true, but of course the universe is expanding. One way you could talk about this is the average expectation number of the baryon number in a thermal state is given by the trace of e to the minus beta h times the baryon number, where beta is 1 over the temperature. And then you can do this little trick of introducing the CPT operator and its inverse, use the fact that the trace is cyclic, and use the fact that CPT in the Hamiltonian commute. That's a very important thing about Lorentz invariant field theory. And then you can write it this way, and CPT acts on baryon number with a minus sign, and so you get that this is minus that, and therefore the expectation number is 0. It's the same statement that nothing happens in thermal equilibrium. Another way to say it is that the number density of a particle species in thermal equilibrium is essentially given purely by its mass. Okay, if you write down the distribution function, it's given entirely by its mass in the absence of some chemical potential. And the mass of particle and antiparticle are the same by the CPT theorem. Therefore, the number densities are equal. So you need to violate the baryon number symmetry, you need to violate discrete symmetries, C and CP, and you need to get out of thermal equilibrium. If you don't do these things, you will not generate an excess of matter over antimatter. Okay, so let's see how you can do this in specific models. The first thing that people tried was grand unified baryogenesis, partly because when people started thinking about this, grand unified theories were a very hot topic, but as you'll see, also because they do provide a rather natural setting for producing matter. So what's a grand unified theory? Well, I'm going to come back when I talk about the electroweak theory and write down some Lagrangians, etc., etc. But here I just want to talk about the symmetry structure. The standard model of particle physics is the strong interactions times the electroweak interactions, which gets broken down to electromagnetism at low energies. But the idea of grand unification is, of course, that at high energies, or if you like, at high temperatures, something else I'll talk about in a little while, this symmetry group is subsumed within a single interaction, a single higher symmetry group that unifies all these different interactions. Now, in the standard model, there are quarks and there are leptons. Quarks carry baryon number, the leptons do not. But if you want to put these interactions into a single group, then you're going to have to take quarks and leptons, and they're going to appear in the same representation of whatever this grand unified gauge group is. Now, if that happens, then automatically there are going to be gauge bosons in the theory that allow you to change which values, which members of this representation of the grand unified gauge group you're in. In other words, there will be gauge bosons in this higher group that will allow you, will mediate interactions that change baryon number into lepton number, etc., etc. So, baryon number violation is a natural feature in grand unified theories. C and CP violation are very easy to build into the theory and be consistent with observations today, and I won't say anything more about them here. Departure from equilibrium is interesting. If the grand unification idea is correct, then you know that the electroweak theory, something we'll talk about in a little while in detail, becomes this SU2 crush U1 theory at about 100 GeV or so. If this is naively extrapolated up to a gauge group, this happens at around 10 to the 15, 10 to the 16 GeV. And at such high temperatures in the universe, the cosmic expansion was much, much, much faster than any particle physics interaction rate. And therefore, when these gauge bosons are decaying in different ways, changing the number of baryon number, the amount of baryon number in the universe, their rate is much, much less than the expansion rate of the universe, and therefore those decays are inherently out of equilibrium. And so, one way to say this is that if you have a set of decays which are biased to produce more baryon number than antibaryons, the inverse, where these things combine and give you gauge bosons, won't happen because the products will be split apart so quickly by the expansion of the universe. So, grand unified theories provide an incredibly natural way to think about the way in which the observed baryonism of the universe could happen. Again, I'm just sketching this for now. I'll be much more detailed about the electroweak theory. There are some problems with this idea. One is that if you really want grand unified theories to work, then of course the universe has to be hot enough for the grand unified gauge group to be relevant. And if that happens, it means that after inflation you need to reheat the universe to such incredibly hot temperatures. And of course, one of the nice things about inflation was that it was supposed to dilute away unwanted relics from the gut era. Now you run the risk of regenerating them. Valentino, moduli, topological remnants, etc., etc. It's something to worry about. Maybe not a big deal that it is the way the world works, but it's extremely very hard to test these things experimentally. You can't probe the gut scale in colliders. And the final thing, the electroweak theory, as I'll show you soon, violates baryon number. And one thing that can do is that if you have a beautiful grand unified theory that generates the baryon number, then along can come the electroweak theory and completely erase that. And we'll talk about how that happens soon. Now, there are ways around these problems. If you want to ask me afterwards, ask me how preheating in the early universe can get around this problem. You can choose a gut that violates P minus L and hence doesn't get erased by the electroweak theory. SO10 is an example. Again, I'm not going to give details here, but these are the kinds of things I quite happily talk about in private. Now, let me move on to the electroweak theory. So we're going to talk in some detail about how electroweak baryogenesis can happen. So let's start by talking about what the electroweak theory is. So it's a spontaneously broken quantum field theory, non-abelian quantum field theory that's built on the SU2 plus U1 gauge groups. So it has a simple-looking Lagrangian that contains within it quite a lot of complicated stuff. You have a field phi, which is the Higgs field. That's the thing that is going to break the symmetry and going to give masses to the fermions. You have a field here, so let me just write down what these are. This is a field strength tensor of a U1 gauge field, B mu, here. That's hypercharge. And then you've got a non-abelian SU2 gauge field, which is weak isospin. And here's the covariant derivative, where tau is the Pauli matrices, essentially. Okay? Now, there's also fermions in this theory. I'll come back and talk about those briefly. And there's a potential via phi. Via phi is the thing that does all the work to break the electroweak symmetry. So here's via phi. It's a Mexican half potential. I've drawn just 2 directions here, but the Higgs field actually has 4 directions in it. It's a field. It's a potential that looks like this, and its minima are not at the origin. They're displaced. So at 0 temperature, what happens in the electroweak theory is that the Higgs field naturally lies somewhere out here. It has a vacuum expectation value. It's about 250 GeV. And that vacuum expectation value is enough to provide masses for the fermions and to break the symmetry from this SU2 cross U1 down to electromagnetism, which is the only unbroken gauge group that remains from this setup. Of course, you have the strong interactions too that I won't go on about. So this is the background setup. This is the electroweak theory. It's tremendously successful, as you know. And all the many, many parameters that go into the fermionic sector and to the couplings here are tightly constrained by precision tests at colliders over the last 30 years or so. More. Now, why is it that you would think that the electroweak theory will be useful for generating something like the baryogenesis of the universe? Well, if you look at the electroweak theory and you ask, does it violate baryon number? The answer turns out to be quite complicated. You write down that classical Lagrangian I wrote down for you, and you say, is baryon number violated by any term in that Lagrangian? And the answer is no, it's not. Then you do perturbative quantum field theory, which is the thing we know how to do best. You go to the minimum of that Higgs field, you wiggle the Higgs field around and wiggle all the other fields around that minimum. That's what we do when we do perturbative quantum field theory. You compute the quantum effects by computing Feynman diagrams, and you ask, is baryon number violated anywhere in this theory? Is there a Feynman diagram that I can write down which changes baryon number? And the answer is no, there's not. Nevertheless, in the electroweak theory, baryon number is violated, and it's violated because it's an anomalous symmetry. Okay? Anomalous symmetries are symmetries of quantum field theory that are only violated by non-perturbative physics. Okay? And in this case, the non-perturbative physics that's relevant is connected to the vacuum structure of chiral gauge theories. I should have said on the last slide, these gauge theories are chiral, by which I mean there's a handedness to the quarks. So let's explore this in just a little bit more detail. Here's a sketch of the electroweak vacuum. I've drawn some direction in gauge and Higgs space. This is, of course, an infinite dimensional space here. I'm just drawing some direction. And this potential is supposed to go on forever. And this is the energy associated with different configurations, static configurations that you can write down. And what you should notice about this is that the electroweak vacuum is periodic. And in fact, if you didn't have fermions in the theory at all, well, it's true if you do have fermions in the theory too, but it's cleaner to talk about without fermions, then as you move from vacuum to vacuum to vacuum here in gauge and Higgs space, all that happens is that you change your fields by a large gauge transformation. So since this is a gauge theory, you would say, well, what do I care? Gauge transformations are just re-describing the physics. There's nothing important there. However, in a chiral gauge theory, something very strange can happen. The coupling to fermions, if you now let me reintroduce fermions, has what I called an anomaly on the last slide. And what that means is that when you move from one of these vacua to another, the symmetries that anything associated with this chiral symmetry is violated. So if you write down a current that describes baryon number, or a current that describes lepton number, in fact, and that'll be important later when I talk about electrogenesis if I have time, then you compute its divergence, which is what you do when you want to know is something a symmetry. And the answer is no, it's not. This is the number of families. In fact, the current is not conserved by a term that looks like this, where W is the field strength tensor that I showed you earlier, F is the other one, and W tilde and F tilde are the dual field strength tensors. They're obtained from these field strength tensors by multiplication by the epsilon symbol. So the fact that the vacuum of a chiral gauge theory is periodic means that baryon number, lepton number, global symmetries, and you couldn't do this, I should say, for a local symmetry, but a global symmetry gets violated in this interesting way. Now, furthermore, this expression allows you to compute exactly the amount by which baryon number would change, or lepton number in fact, as the system made a transition from one of its vacua to the other. And the way you do that is that you take that expression that I wrote down, you write down the configurations in the different vacua, you perform the integral that I showed you, and you find out that the change in baryon number can be given, I should say I'm choosing a gauge here, which is a technical issue I won't get into, but by the change in what's called the Chern-Simons number. Okay? The Chern-Simons number is given by this integral, where A here are those non-abelian gauge fields that I wrote down earlier. So what you really should take away from this is that if you move from vacuum to vacuum to vacuum in the electroweak theory, then you will change baryon number, and you'll do so in a very precise amount, and F here is the number of families, as I said. And you can figure out what amount that is by just asking, how did the gauge fields change as I moved from vacuum to vacuum, plug them into this expression, and compute the answer via this. That's all you do. I should say that the Chern-Simons number, as you move from vacuum to vacuum, is actually easy to compute and changes by 1 in the units that I've written down. And I'll remark parenthetically that there's a very nice mathematical story underlying this structure in the electroweak theory to do with the homotopy structure of the electroweak vacuum and the fact that its topology is that of a 3-sphere. And if you want to talk to me about that later, I'll happily discuss it with you. But for now, let's just use the fact that we know the amount by which the electroweak theory violates. So that's all very well and good. I hope to have convinced you at least that the electroweak theory that you know and love and describes everything in your body violates baryon number. And now you should worry. Because you're made of baryons, and I've just convinced you that they decay. Now, of course, you don't really need to worry about this. And the reason is that at 0 temperature, which we are at for the purposes of this discussion, the only way you can get from vacuum to vacuum is by tunneling. And if you look at the heights of the barrier between these different vacua, then so I should say, this is an infinite dimensional space that you're looking at here. I've just given you a slice through it. So it's not like just one barrier as I've written here. There's an entire infinite dimensional ridge of barrier between these vacua. But the lowest point on that ridge is a configuration of gauge and Higgs fields which is called the Stauron. This was called, originally coined by Manta and Klinkhammer. This configuration has an energy associated with it. The energy, depending on Higgs masses in the standard model, somewhere between 8 and 14 TeV. And if you do a standard tunneling calculation in quantum field theory, which we'll talk a little bit more about soon, but in this context, all I really want to tell you is that you compute the rate at 0 temperature for doing this, and it's an exponential of a rather large number, which can be written as 10 to the minus 170, where I've omitted units because in any units you care about, that is absolutely tiny. So what does this number tell you? It says that if the universe were always at 0 temperature, not one proton would ever have decayed in the entire history of the universe. So you're okay. You'll at least be able to enjoy this week. Now, that's reassuring, but of course I want to make use of this baryon number violation in order to generate the baryon symmetry of the universe. So how do I do it? Well, at finite temperature, the story changes. How does the story change? Well, if you really want to do this calculation properly, then you have to take the electroweak theory and you have to turn it into a finite temperature effective field theory. And that's certainly not something I'm going to go into in detail in an hour-long talk. But I just want to outline what happens here. The calculation you do is the following. You say you prepare your Higgs and gauge fields in a given thermal state. So you've heated up the universe, and you've prepared them in a given thermal state corresponding to whatever the temperature is. And then you compute the rate to cross the barrier over that Stauron configuration I talked about from that state. Okay. That's the first thing you do. That's a relatively simple thing to do. It's really just that's just a standard calculation. But because this has a finite temperature, there's more than one way that it makes sense to go over the barrier. After all, this is an infinite dimensional system. So, although, I can write one thing on here, you're going from one minimum to another. There's a ridge between them in your infinite dimensional space. There's one way to go over, which goes directly through the Stauron. But there are infinitely many paths that go very close to the Stauron of slightly higher energy. And those are higher energy, so they're harder to traverse. But on the other hand, there are very many of them. And so there's an entropy factor here that's important. So you have to add up the effects of all these paths. Okay? And you have to weight them by the Boltzmann factor. So it's quite a tricky thing to do. And you also have to take account of the infinity of directions that are in other directions to the Stauron as well. And that corresponds to calculating a small fluctuation determinant around this configuration. So needless to say, this is a rather complicated finite temperature field theory calculation that was perfected really only over a number of years by a large number of authors. But the bottom line is that the finite temperature rate of baryon number violation has a prefactor in it that involves the temperature. This MW also involves the temperature. And is suppressed by an exponential of this form. Now, what goes into this exponential here are two things. The first one is the temperature itself, which is what you'd expect to see in a Boltzmann suppression. The second is the energy of this configuration here computed at finite temperature. And the hotter the system is, the easier it is to jump over this barrier, and therefore the effective energy height of the barrier is decreased. So we'll explore this in a little more detail in a moment, but the rough idea here is that the hotter the system is, the lower this barrier appears, the less the suppression of baryon number violation. Furthermore, at very high temperatures, temperatures higher than the critical temperature of the electroweak phase transition, which I'll talk about soon, the barrier just goes away, it becomes irrelevant. And the rate per unit volume of baryon number violation takes this form. It's given by alpha weak, which is about 1/30, to various powers, temperature to the 4th, and a constant, which is numerically obtained to be about 30. Okay. So roughly speaking, numerically, it's alpha weak T to the 4th. The hotter the system is, the more rapidly baryon number is violated. So the message of this slide and the previous one is that in today's universe, baryon number is never violated in electroweak theory for all purposes that you care about. There was a period when the universe was close to, say, 100 GeV, when baryon number was being violated by an amount that was suppressed, but not too suppressed. And then at temperatures hotter than 100 GeV or so, and we'll get to the precise number soon, then baryon number was just happening all the time in electroweak theory. You know, lots of processes producing more baryons than antibaryons, lots of processes producing more antibaryons than baryons. This just happens copiously at high temperatures. Now, it helps to have an analogy in mind when you're thinking of the system, because after all, I'm speaking about an infinite dimensional system. It's a field theory, it's a finite temperature. There are fluctuations in this infinite dimensional space. You're calculating fluctuation determinants. It's a messy, messy calculation. There's a nice analogy to think of that I think is helpful to have in mind and helpful to refer back to when you're thinking of this system. So here's a system that you all know. It's a simple pendulum. So here's the Lagrangian for a simple pendulum. It's got mass m, it's being acted on by gravity, length L, displacement theta. You've seen this before. If you haven't, you're in the wrong room. Now the Lagrangian is given this way, and what I really care about is the potential. And the potential is periodic, which is exactly the way I described the electroweak vacuum. So how do you solve a system like this? Well, first of all, you could isolate the vacua where the potential vanishes. And where the potential has a minimum, I should say. And there are infinitely many of them, as there were in electroweak theory. And the periodic potential, if I were to take this system now, quantize it, and solve it, and I should say you can actually do this system exactly that I want here, then you would find that this periodic potential guarantees that your wave functions will be periodic. How could it not? Okay. So that's fine. That's what you would get. This is, of course, not what we do usually for physical systems. What we really do, particularly in quantum field theory, where we don't know how to solve anything most of the time, is we do perturbation theory. So if you want to do perturbation theory, you make a few new definitions here, just to simplify the system. I'll halve my angle, I'll define this frequency, I'll define a coupling in this way via h bar, and I'll take the Schrödinger equation that I would write down for this Lagrangian, and I'll write it that way. Now, as I average down here, it's got a periodic term that appears, and therefore the wave functions will be periodic. But as I said, we don't really do this. What we really do is we take an equation like this, and in the context of quantum field theory, we take some horribly complicated system, and we say, that's too hard. So let's pick a minimum, and let's expand about that minimum. So in this case, let's pick the minimum at n equals 0, theta equals 0. We take the potential, and we expand it out. And we'll keep only the first term, which is chi-squared. And now you know what this equation is. It's the Schrödinger equation for a harmonic oscillator. You knew this was coming anyway, of course, because you know that for small angle, this is just a harmonic oscillator, but now you see how it arises here. And then you would go ahead, oops, that's not what I want to happen. You would go ahead, and you would now know for small angle perturbation theory what the quantum mechanics of this system was. Now, this is, of course, a zero temperature calculation. Okay? When is it valid? Well, it's valid when you're considering energies that are much, much less than the barrier height. The barrier height here is the energy of the configuration when the field's sitting up here. That's the energy, the maximum energy you would need to get all the way around from one vacuum to another. If you never have that energy in your system, you don't care about the fact that there are multiple vacuums. In this approximation, you lose the periodicity completely. And it only affects, the periodicity only affects high energy physics when the barrier cannot be ignored. But at high temperatures, if I start to heat this system up now, what will happen? Well, that pendulum, rather than sitting at the bottom here, will start to get kicked around by thermal fluctuations. It'll be coupled to the thermal system it's in. It'll start to wobble around. I start to heat the system up, it will get increasingly large kicks from interactions with a hot background. And sooner or later, the energy of thermal fluctuations will be so large that it will be able to just randomly go all the way around one direction or another. It will be able to fully probe the non-perturbative structure of the potential. This quantum mechanical approach will be irrelevant, and I'll really need to know everything about the system. And in fact, if I took this system and I added one small component to it, namely, I put a little counter at the top, and every time the pendulum went that direction, I counted 1. Every time it went in that direction, I counted -1. Then this would be an extremely good analogy for baryon number violation in the electroweak theory. I would be making transitions due to high temperatures from one vacuum to another, and as I do so, I'd be adding baryon number. I could go the opposite direction and add anti-baryon number. And in fact, if this system had a slight bias, taking it more one way than the other, that would be a very good analogy for the effects of CP violation in the electroweak theory. So this is a good thing to keep in mind. Eric?
So in this case, though, you only have the path that takes you exactly along this failure.
That's right. That's right. That's right. So that's precisely why I wanted to use this analogy, because this picture that I was sketching here, and I got into in the last slide, it's extremely important in the electroweak theory for getting the numbers right. But it sort of masks the simple picture of what's going on. Namely, you heat up the system, and sooner or later, the system is insensitive to the fact that it has multiple vacua and just freely, winds up the gauge field and the Higgs field in any way it sees fit, and thereby changes the baryon. So this captures that setup here, but indeed, the actual calculation we would do here would be a much simpler one. Even at 0 temperature, the calculation is a much simpler one. You just compute the tunneling rate, whereas in the standard model, you have to go ahead and compute the right instantonics. So this is a useful analogy for many features of the electroweak theory. So to summarize the electroweak vacuum, it's periodic, as I said. There are barriers, which are called sphalera, and every time you move from one vacuum to another, you add a complete combination like this. An up, 2 ups and a down, an electron, 2 charms and a strange, a muon, 2 tops, and a bottom and a tau. You change baryon number by 3 units, and you change lepton number by 3 units whenever you do this. So I've just added numbers here to the picture that I showed you on the last slide. This is the net effect of that change in Chern-Simons number as I move from vacuum to vacuum. Yeah?
What would you produce for mass and whatever?
I haven't got to that. So the question was, why would I produce more matter than antimatter, and not the other way around? So in the previous slide, what I tried to say is that if you just take my analogy, you wouldn't have the pendulum go more one way than the other on average. But if you added a small bias, then you would. And that bias in the field theory example will be CP violation. So if you have CP violation, it will bias slightly in one direction. We'll get into that a little bit more. Yeah. So for T bigger than some critical temperature, which I'm calling the electroweak temperature, things become very interesting, as I said, and baryon number violation is unsuppressed and copious, in fact. So let's get on to CP violation. As you say, why would I bias in one direction rather than the other? Now, in the standard model, C is violated maximally. It's a chiral gauge theory. I'm not worried about C being violated. But what about CP violation? Well, it's definitely there. In the standard model, if you take that Lagrangian that I wrote out, and you isolate the following term, this charged current interaction. So UL here is the quarks, is the up type quarks, and D is the down type quarks. Then there's a coupling between them that looks like this. This is what's called a charged current interaction. Okay? Now, I've written it here in what's called a weak interaction basis, literally in terms of the quarks, which are the things that interact in the weak interaction. However, there's another term in the Lagrangian that describes the masses of these objects. And that is not something that is diagonal in this basis. And that tells you that if you produce these particles, you don't produce them in the basis that this interaction is written down. If you want to know the right way to think about the quarks in this way, you use unitary matrices to diagonalize the mass matrix. So if I took the matrix of masses of the up quarks and the matrix of masses of the down quarks, I can make them diagonal, just mass up, mass charm, mass top, mass down, mass strange, mass bottom, by just diagonalizing with these unitary matrices here. It's just a very simple diagonalization problem. But if I do that, and I ask, what form does this interaction take, then I have to rotate the basis into these primes, and then I get this term. And now, rather than just having this straight interaction, there's a matrix that appears here in this interaction. And that matrix, which you can see just by using this substitution in here, is given by this, is what's called the Kobayashi-Maskawa matrix, or the Kabibo-Kobayashi-Maskawa matrix. And it describes these interactions. And in the standard model, you can ask what degrees of freedom are in that matrix, by which I mean what possible types of interaction are allowed. And it turns out that for 3 generations, which is what we think we have, as in the standard model, there's precisely one independent non-zero CP violating phase in this matrix. So the standard model interactions, all on their own, contain the possibility of CP violation, and in fact, it's that thing that you would hope would bias these interactions one way over the other. That's really great news. However, it's not perfect news. This CP violation, which I told you is in the CKM matrix, and experimentally we believe is seen in the KM system, for example, is insufficient to generate the baryon symmetry. It's too small. This is something we measure. So you have to turn to extra sources. So to give you a simple phenomenological example of how this might work, if I had some interesting higher order term in my Lagrangian, which connected my Higgs fields to my SU2 gauge fields, like this, certainly something I'm allowed to write down. And you'll remember that these gauge fields can be written as connected to baryon number. And so I can actually write this term by integrating by parts and assuming that things are nicely homogeneous in the following way. So I've used the fact that this combination of gauge fields is related to baryon number. And now what you can see is going on in this term is that, oops, this acts like a time-dependent chemical potential for baryon number. So if the Higgs field changes rapidly, then baryon number will get biased in one direction or another. This will only happen if I have extra sources of CP violation in my theory. It won't happen on its own. So are there 10 minutes to the hour? How long do I have? Until the hour? Okay, great, thanks. So I'm going to actually skip this slide there for you. Let me go on to the departure from equilibrium. So I told you the standard model has interesting behavior at non-zero temperature. Let's explore this a little bit further. So I'm not going to do detailed finite temperature field theory. Let's do things in a quick and dirty way. Let's look at a toy example. Here's a scalar field with a spontaneously broken potential here at 0 temperature. And all I've done is couple it to another scalar field, which has its own kinetic term and a coupling to phi. The reason this is an interesting example to look at is you can ask the question, what if this field chi is sufficiently light that's in thermal equilibrium? And its interactions with phi therefore describe the interactions of phi with a thermal bath. If you do that, you can just replace chi by its average value, which will be the temperature, because it's in thermal equilibrium. And then you know that you can replace the potential, a 0 temperature potential for phi, by a finite temperature one that will look just like this. This is just a toy example. What you've seen here is that immediately as I take a field and I put it at finite temperature, it allows the fact that there's a critical temperature in the system at which the mass term changes its sign. So at this value of the temperature, the mass term changes from being a positive mass term to a negative mass term. That means that in this system, there's a simple phase transition. At high temperature, low temperatures, you have a vacuum expectation value for phi, because it's a spontaneously broken potential. And at high temperatures, you don't. The symmetry is restored. And this happens in the electroweak theory also. But in this example, the phase transition is continuous. Sometimes people say second order. Namely, as the temperature drops, the field essentially rolls down its effective potential to a non-zero value. It's a very calm process. The departure from equilibrium here is not very high at all. So even though there's something happening to the system at finite temperature here, you don't depart from equilibrium in any very strong way. Fortunately, in the standard model, if you carefully compute the same potential, integrating out and allowing for the interactions with gauge fields and other light fields in the system, and you ask, what is the potential that describes the Higgs field in the Standard Model? The answer is somewhat more interesting. It has a bunch of couplings in here, it has a top quark mass, and it has a term just like the one I wrote down in the toy example. There's a 5 to the 4th term that's always there, but interestingly, there's a cubic term that gets generated, particularly from integrating out these gauge fields. So this system has a critical temperature, which you could derive, above which the symmetry is restored, below which it's not. But what's interesting about this is the way in which the system goes from having its symmetry broken to being restored. And it does so like this. At the critical temperature, there's a barrier that separates the false vacuum from the true vacuum. And as we'll see, if this cubic term is present and large enough, then a strongly first-order phase transition happens, which is very, very useful. So what happens is this. At very high temperatures, the electroweak symmetry is restored. At low temperatures, it's broken. The Higgs field gets an expectation value, gives masses to the elementary particles. And at a critical temperature, the phase transition occurs. And the order of this phase transition depends on the presence of light scalars in the theory, the Higgs field in particular. And I'll just tell you that for successful electroweak baryogenesis, for this to be strongly first order, so that you get a large departure from equilibrium, and to avoid something called washout that I may mention soon, the only light scalar in the minimal Standard Model is the Higgs. And if you want this to work, the Higgs needs to be lighter than 80 GeV. And those of you who have paid any attention to particle physics in the last 20 years will know that the Higgs is known from precision measurements at LET to be heavier than about 114 GeV. So in the Standard Model of particle physics, not only is there not enough CP violations, the phase transition is a continuous one, like in my toy model, is not sufficient to give you a departure from equilibrium. So we need more. I already mentioned how we get more CP violation. You go to side extensions of the model. And we're going to do that here in the Standard Model in a moment. Before I do that, let me just tell you how this phase transition completes. If you have a first-order phase transition like this, then at a critical temperature, bubbles of the true vacuum, this here, start to nucleate in this false vacuum. And what happens is you get bubbles here, so the ambient space here is all in the unbroken phase. The bubbles are bubbles of the true vacuum. The bubbles start to expand. They collide with each other. And as they pass through space, they convert true vacuum to false vacuum. And as they do so, if the phase transition is strong enough, there's a very large departure from thermal equilibrium in this system. And it's that departure that allows you the possibility to produce more matter than antimatter. Okay. It's the boundaries of the bubbles as they spread through space. Okay. So there's a possibility here that as these bubble walls fly through space, converting false vacuum to true vacuum, that every point in the space can become a site where you have a chance of converting wall baryons to antibaryons or vice versa. If you do that, you have to be careful. In the rest frame of a particular point in space, the wall comes along. It converts symmetric phase to broken phase. You've got lots of baryon number violation, but after the wall's passed, you want there to be none. Because if you still have baryon number violation in the broken phase, then you'll erase this nice baryon symmetry you've produced. So behind this advancing bubble wall, the expectation value is not quite the zero temperature expectation value. It's the expectation value computed at finite temperature. And what washout means is that the baryon number violation has to be small here. And to figure out if it's small enough, you go back to something I showed you quite a few slides ago. You take that finite temperature rate, and from this you can figure out quite simply that if the expectation value behind the wall has this relation to the temperature, then baryon number violation computed via this is small enough that any baryon number you produce as the wall passes a point in space is frozen in. So how does the baryon number get generated? So I don't want to go into detail about this particular part, but I just want to mention it as a possible thing we could discuss in our discussion sessions. But the actual dynamics as a bubble wall passes a point in space is quite complicated. The wall starts moving forward. If you do a calculation of how a bubble wall moves in a phase transition at in a zero temperature field theory, then the wall's immediately move out in the bubble. They reach very close to the speed of light very quickly. In an electroweak plasma, it's a little bit more complicated. They start to plow into the plasma and they reach a terminal velocity, which is some fraction of the speed of light, somewhere between 10th and 100th of the speed of light. And as they do so, they burst into the false vacuum, converting false vacuum to true vacuum. Particles bounce off the wall. They experience the changing Higgs field. As I showed you in the CP violation slide, that changing Higgs field sources the production of more baryons and antibaryons. Then the wall passes. As it does so, you now enter the true phase, the broken vacuum phase. A baryon number violation shuts off. And this excess of baryons over antibaryons that we produced is locked in. So that's the idea. So let me skip this slide since it's technical. Okay. What's the final number you get from a calculation like this? Well, this is just a sample calculation done using not something concrete like the minimal supersymmetric standard model, but just an extra bit of CP violation thrown in as a free parameter. So you get a CP violating phase. This is the number I'm looking to calculate, the thing I call eta. You get masses of the leptons that are important because they're bouncing off the bubble walls. You get diffusion constants that tell you how particles diffuse in the plasma ahead of the wall and behind the wall. And then you have the wall velocity, and that's why it matters how in a really physical situation this wall propagates through the plasma. So I'll just say that for the right values of these constants, then obviously you can get the correct order of magnitude to explain the baryon asymmetry. The question is, can you get the right values of these constants in a meaningful particle physics model? So are there extensions to the standard model that do this right? So I'm almost at the end, but let me point out one thing. If I go to the minimal supersymmetric standard model, which is the simplest extension of the Electroweak model. So I spent all my time here telling you about how this works in the standard model because it's a very simple, clean system. In the minimal supersymmetric standard model, it turns out that that number that I just showed you how to calculate can be actually generated to be 10 to the minus 10 if you have the following things true. You have a like Higgs, a like top squark, which is the supersymmetric partner of the top quark, and obviously you need enough CP violation. This is very promising for the Large Hadron Collider, and in fact future colliders, because like Higgs, you certainly know will be in their energy reach. The only problem there is that it takes a few years to get enough data to figure out that it's there. So what is the exclusion round? It's this. This is the Higgs mass, the lightest Higgs. This is the right-handed stop mass. And the only thing you need to take away from this plot is not so illuminating, is that the Higgs needs to be somewhere in the less than around 120 to 130 GeV, and the lightest right-handed stop needs to be less than around the top quark mass. And these are both very, very close to current experimental values. So the LHC should provide us with a lot of data that allows you to tell you definitively whether the MSSM is the source of baryon asymmetry. So I think I'm going to skip to the end here, since I'm running out. So most of what I've had to say today is to try to convince you that this is a central issue in particle cosmology, where the origin of the matter-antimatter asymmetry came from. Even though we talk about the energy budget of the universe in terms of the dark matter and the dark energy and what are they made of, and I'll have a lot to say about that in the next two talks, even the things we know a lot about, baryons, are a complete puzzle. We do not know why they're there at all in the universe, and in particular why they're there in sufficient amounts to make us and galaxies and planets and other things. I've tried to talk about the well-developed examples here. In particular, I focused on the electroweak theory, which has the advantage of being testable at upcoming colliders. And the whole point of these models, of course, is that they use physics of there for other reasons. The MSSM is not invented to make baryogenesis work. People are interested in it because it solves the hierarchy problem, because it provides a nice completion of the electroweak theory. If it also provides us with baryogenesis, and as we'll see next time I go talk dark matter, that would be quite remarkable. So there's a lot of upcoming evidence in future colliders. And there are some references here that I provided earlier. Thanks.
Okay, we have time for a couple of questions.
Do you know the current constraints on the Higgs mass and
100, yeah, so
if this is compatible with what you say?
yeah, so there are two sources of current constraints on the Higgs mass, right? There's the lower bound that comes from lap method. Lap has been done for quite some time now, right? So that's 114 GeV or so. And then there's the bounds at higher masses, around 170 or so, I think, 160, that come from the very latest Tevatron results, where they've managed to just get enough integrated luminosity to dip below the constraints. That's interesting for other reasons, but not for this, because already at those masses, this cannot work in the MSSM. In extension to the MSSM, it's possible that those could be interesting constraints, but here in the MSSM, they're not.
And would you mention some words about inflation at the electroweak scale?
Will I mention it?
No, if you would like to mention something about that.
So there is, of course, right. So one thing I said when I talked about gut baryogenesis is that you do need inflation to get you hot enough to reach the gut scale in order to get that to work. And there are all sorts of associated problems with doing that. Now, another possibility is that inflation happens at a low scale, at the electroweak scale. If that's true, there are sort of pluses and minuses of that. The plus is you better have reheating be hot enough to get you above the electroweak scale, because if you don't, it's very, very hard to get any kind of baryogenesis to work at all in the universe. The one way in which I know to make it work around that scale is to use this thing I referred to obliquely called preheating, the fact that the universe, as it reheats after inflation, need not do in a very calm way, but can do so in a very non-thermal way. If you do that, it's possible that even though the reheat temperature is low, that you can kick enough energy into certain particles to make either, if you like, configurations that look like the sphaneron or heavy particles that then decay. And because of the way they're produced, they're automatically out of equilibrium. It's possible to make it work that way. It's something I definitely happily talk about in the discussion section. But it's certainly a different picture to what I talked about here, because the universe is not smoothly passing through the electroweak phase transition in that case.
So I think this is interesting, but in terms of the observational side, I have a question. So you said that we might see signatures at the LHC that tell us some parameter values, and then we can calculate whether baryogenesis could have happened within supersymmetry or something. And then the answer is yes or no. But is there more?
Well, so it's not just, the thing about, right, so the hard thing about baryogenesis, if you just think about it in isolation, is it's a number that you're trying to calculate. That's it. The more interesting thing is that any reasonable particle physics model that you hope to do it has to obey all the other constraints that come into that model as well. In the case of the MSSM, for example, there are a host of different things that have to be right and that you have to find at colliders. It's not just a number. Of course, the endpoint of the baryogenesis is. You need the Higgs to be the right mass. You need the lattice stop to be the right mass. And if those are right, then you would have some confidence that the phase transition proceeded in the way that you thought it did. But then you need to figure out what happens with the CP violation. And so that also requires you to look for the terms that I showed you that can happen, I didn't really go into, but that can arise in the MSSM. Yeah, CP value in terms that can come in the genome mass matrix, or can come through phases between the Higgs doublets that arise in the model. Those have to have the right couplings. They have to appear with a big enough sign that you can get the right baryon temperatures. And those have their own signatures, typically in B physics. So they change the branching ratio of beta S gamma in ways that you'd expect to see in B experiments. So there's more than one thing to do. But once you've done that, then it's a matter of whether the theory itself is consistent with all other measurements. There are not other signatures of baryogenesis that I know of, which I think is partly what you're asking.
Yeah, I guess I'm just wondering if all the input comes from the collider experiments and then the output is the calculation of cosmology, like there's no...
You're asking is there an observational cosmology observation you can do?
Yeah.
Yeah, not that I know. No. Absolutely not.
here then.
There's one more question if you want that she was waiting for.
So actually, the question I wanted to ask is probably something you can answer later, but I wanted to throw it out there, which is, what does an open sort of question look like in this context? So when people are thinking about MSSM, what are they thinking about if you're trying to formulate a question? I think for this audience, that would be
I
useful.
can definitely get to that in the
So in the discussion, I think that would be useful. And then I guess I also wanted to ask which of the references would be good for finite temperature calculation to understand sort of the details of that. So you can also answer that.
Yeah, I can do that.
Okay, so we stop here. We thank